Okay, so now that we've talked about the basic rational function, we want to talk about what if things get a little more complicated. So a rational function is an equation where you have like a function in the top and a function in the bottom. And that's what this means, where you have a of x over b of x, and b of x can't equal 0. So this is a lovely example of a rational function. They are not continuous like so many other of our functions that have had a domain of all real numbers, because if there's an x in the bottom, you might have an asymptote. And so a vertical asymptote is when you have a rational function when the denominator equals 0. So like on this one, we would say x equals -3 would be a vertical asymptote. So that would mean in our domain, we would skip over -3, right? Like it would be like -infinity to -3, and then -3 to infinity. It just like jumps over it. And so we've talked about our log graphs that have vertical asymptotes, but if you have an x in the bottom, you're also going to have a vertical asymptote. And so the other thing that you can have is you can have a horizontal asymptote. And so a horizontal asymptote is when a graph, okay, so let me just kind of draw this for you here. Think about our good old y equals 1 over x graph. When you graph that basic function, it looks like this. So the vertical asymptote is that line here. The horizontal asymptote is the horizontal line that your graph never touches. And so in this case, the vertical asymptote would be the line x equals 0. The horizontal asymptote is the line y equals 0. And so that means when x gets really, really big, what's happening to y? That's what the horizontal asymptote is. And so for the vertical asymptote, you just set the denominator equal to 0. But for the horizontal asymptote, it's all about the degree of the numerator and the degree of the denominator. And so if you think about it as like a to the n on the top, let's do a x to the n over bx to the d for numerator and denominator. If it says f of x has at most one horizontal asymptote, if the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptote. So if numerator is bigger than the denominator, and remember degree is the exponent, if the numerator is less than the degree, then it will always be the line y equals 0. And that's like this one. The numerator degree is 0, but the denominator has an x in it, and so that's going to be the line y equals 0. And then the other case is if the degree of the numerator is equal to the degree of the denominator, then it's going to be the leading coefficient of the numerator over the leading coefficient of the denominator. So let's look at these examples so I can show you what I'm talking about. So you don't have to label them as vertical and horizontal, because remember that an x line, x equals a number is a vertical line, and y equals a number is a horizontal line. And so that's what gives you the answer. You just have to know how to find it. So to find the vertical asymptotes, you just set the denominator equal to 0 and solve it. So on this one, my vertical asymptotes are going to be at what makes this equal 0. That would be at x equals -1. My horizontal asymptotes, there's not really any math to do, but you have to know these rules up here. So you have to know the degree of the numerator over the degree of the denominator. So the degree is the highest exponent. So on this one, the highest exponent is 2 on top, and on the bottom, the highest exponent is 1. So when the numerator is bigger than the denominator, that's no horizontal asymptote. So there's none. No horizontal, I'll say. So what about number 2? Vertical asymptotes. You set the denominator equal to 0 and you solve it. I would just add 1 and take the square root. So you actually get 2 vertical asymptotes on this one, both +1 and -1. And what about the horizontal asymptote on this one? The degree of the numerator, there's no x up there, so that's a degree of 0. And the bottom has a degree of 2. So if there's an x on the bottom and not an x on the top, that's always going to be like that parent function, which is y equals 0. What about the third one? Vertical asymptote. If I set the bottom equal to 0, that would be the line x equals 3. And this is the example of the third option. The degree of the numerator and the degree of the denominator are the same. And so I just take the leading coefficients, which happens to be 2 over 1. And in this case, it would be a horizontal asymptote of 2. Okay? The other option that could happen is instead of having a infinite discontinuity, which is what an asymptote is, you could have something called a point discontinuity. And a point discontinuity is not a line that your graph never touches, it's just like a hole in the graph. And an easy example of that is if you have an equation that you can cross something out in both the numerator and the denominator. So on this equation, I factored it already for us, but look at this. I could cross these out, which means the simplified version of this is just the line x equals, or y equals x minus 1. But we have to say that x can't equal -2 because in that original problem, the domain would restrict me to not having -2. So let me show you what that looks like when you graph it. So first of all, graphing the line x minus 1, hopefully you feel pretty good about that. That's just slope-intercept form, right? That has a y-intercept of -1 and a slope of up 1 over 1, up 1 over 1. But when I go back here at -2, because I crossed it out, it's undefined there at -2. So when I go down 1 and back 1, that would be a -1 for x. Down 1 and back 1, that's going to be a little hole in my graph that's undefined. That's called a point discontinuity because it's undefined in that one little spot. Instead of the whole line being undefined, it's just like that. So how do you tell the difference between a discontinuity as a point or a hole in your graph versus an asymptote? It's all about whether it cancels out or not. If it cancels out, it's a hole. If it doesn't cancel out, it's an asymptote. So look at this one. It says determine all asymptotes and the values of x for any holes in the graph. So in order to know the difference of whether it's an asymptote or a hole, you have to be able to factor, okay? So the first thing I'm going to do is I'm going to check to see if it's factorable on both the numerator and the denominator. So what multiplies to give me 6, that adds to give me 5, that would have to be 2 and 3. And on the top, that's the difference of two squares. So I can factor that into x minus 2 and x plus 2. Vertical asymptotes are things in the bottom that don't cancel out with the top. So the fact that right away I can see that I can cancel out the x plus 2, that means that at -2, that is just a hole in the graph or a point discontinuity. But x plus 3 does not cancel out, so that is an asymptote. So when I graph this, which would be really ugly to graph, at -2 there would just be a little open circle in my graph, but at -3 there would be that dotted line that my graph isn't touching. X minus 2 is nothing. It's in the numerator. It's not restricted. You can have 0 in the numerator. You can't divide by 0 in the bottom. Okay, so the last thing we want to put together is we want to talk about, okay, how do I graph these? Which is a little bit more complicated than what we graphed in 9.3. So here are my suggestions. One, you find your asymptotes first because your asymptotes give you a shape of your graph, and then you plot points in each interval. And so I picked kind of a crazy one here. Why did I do that to start with? I don't know. But we're going to at least start with the asymptotes, and then maybe we'll finish the graph in class. But asymptotes first. So I'm going to factor the bottom here. What multiplies to give me 6, that subtracts to give me +1. That's also 3 times 2. It'll be +3 and -2. So right away, I know my vertical asymptotes are at -3 and +2. How do I know it's not a hole in my graph? Because on the top, I can't factor anything out, so it's not going to cancel out. So what does that mean? It means on my graph at x equals -3, I can draw a dotted line that I know my graph will be in between. Or my graph will never touch, sorry. And at x equals 2, I can draw a line that my graph will never touch. The other thing I want to do is I want to find my horizontal asymptotes, and this is where you have to know about the degree. The degree of the top is 1, the degree of the bottom is 2, so that means that my degree is, the top is smaller than the bottom, so that means that the x-axis is my horizontal asymptote. So now the hard part is we have to pick points. And this is where you're going to have to plug stuff in. Here's my advice. You always pick points outside the the asymptotes, and since this one has two asymptotes, you also have to pick what's in the middle. Just like what we did in 9.3, the outsides are going to be those like L-looking shapes. So as long as you can kind of figure out where to start, you can get those. The middle is going to be a little bit more complicated. So how about you pick a few points and see if you can get what the Y values are, and then we'll go from there. What would I pick? I would pick the point right next to my asymptote out here. So that's at -3, so I would pick -4. And honestly, whether it's up here or down here, then I can use my asymptote as a guide. I would do the same thing over here. I would pick +3 to see where it's going to go. And then in the middle, I'm going to have to do a little bit more work. Like I'm definitely going to pick like -1, 0, and 1. And depending on what happens, I might have to pick more. And this is where you have to really use your calculator correctly to do this. So please try this, and we'll talk about it in class. It's a new